My name is Michael Crump, and I'm a Material Science and Engineering graduate student at the University of Washington. In addition, I am a 2015 graduate fellow of the Clean Energy Institute at the University of Washington. Today, I'm going to introduce Energy Dispersive X-ray Spectroscopy, or EDX for short. EDX is generally used for compositional mapping, for us to understand the composition of a given sample. And typically these samples are thin films. Not only can relative amounts of each atom be measured, but the distribution of the atoms in our samples can be mapped. Because EDX is an extension of the Syrian Scanning Electron Microscope in University of Washington's Molecular Analysis Facility, make sure to watch our SEM videos before continuing. This video is not intended to be a review of all the capabilities of EDX, but I'll introduce the underlying physical concepts of EDX and then show step by step how I use EDX in my solar-related research. So, how does EDX determine the composition, or in other words, differentiate between atoms? In general, atoms are composed of nuclei, protons and neutrons, with electrons orbiting around them at different energy levels. During SEM operation, a high energy electron beam impinges on the sample. Some of these electrons collide with electrons residing at lower energy levels in the atoms, and then both electrons scatter and leave the atom. As a result, an electron located at a higher energy level sees the vacancy and jumps at the opportunity to reside at this lower energy level. When the electron falls down to this lower energy level, it releases energy, specifically X-rays. Because these electron transitions are characteristic of the specific element, the energy of these X-ray emissions is also characteristic of the element. You'll also see that multiple electron transitions for an atom are possible because electrons can fall from different elevated levels. Most elements of the periodic table are detectable. Elements lighter than beryllium have energy transitions that our EDX detector cannot detect. Also, noble gases generally cannot be detected in a meaningful manner because they typically don't form solids with other elements. So, what exactly happens when X-rays are emitted from the sample and detected? First, an X-ray must enter through an aperture in the collimator assembly to ensure only X-rays excited from the sample are detected. Then, an electron trap in the form of a pair of magnets is used to prevent stray electrons from reaching the detector and creating artifacts. Then, a polymer window is used to maintain a high vacuum within the detector while still allowing X-rays to pass through. Finally, X-rays that reach the silicon crystal generate a charge pulse that is amplified by the field effect transistor, or FET. The amount of charge is directly proportional to the characteristic energy of the X-ray, meaning we don't lose that information. A cryostat is used to cool the detector, which reduces the noise, therefore increasing our signal-to-noise ratio. The generated pulse is then passed onto a multi-channel analyzer that displays a plot of X-ray intensity versus X-ray energy. Why are perovskite solar cells an interesting research topic? Perovskite solar cells have achieved a certified efficiencies of over 20% in the past 5 years, skyrocketing past other alternative solar technologies. What is especially exciting about this technology is that these perovskites are solution processable in ambient conditions, meaning it could be possible to prepare inks of our precursors that are then printed or coated and then subsequently dried in a manner similar to printing a newspaper. This would be a much less expensive manufacturing technique than how we currently make silicon-based solar cells. What are perovskites exactly? Perovskites are basically a crystal structure, and in this case, we're referring to organic-inorganic hybrid perovskites. The most common perovskite, methylammonium lead iodide, or MaPbI3, is composed of inorganic lead iodide cages that trap the organic methylammonium molecules. These perovskites excel at absorbing light and transporting charges generated by light, two properties that are necessary for an efficient solar cell. All right, so here is the perovskite film that I was referring to earlier. We can see here that the film is generally brown, which suggests that it's a good absorber of light. And we can also see that's a bit shinier and metallic than you'd expect. This is actually because I've sputtered some palladium and gold on top of it to ensure the film is very conductive, because that's important to making getting a good SEM image and doing a good EDX experiment. All right, so next I'm going to load the sample in the chamber, and then I'm going to basically raise the stage and focus the image. You should see our previous videos to see in detail how we do that. For now, we're going to jump ahead to the actual EDX. So what we're doing here is basically just venting the chamber. Before it was under vacuum, and now we're just filling it with nitrogen to bring it back to room pressure, ambient pressure, so then we can load our sample. So now the chamber is vented, we can open it now. All right, and now I'm going to put the plate in the sample holder and tighten the screw to make sure the plate doesn't move anywhere. All right. Now I'm making sure that the sample isn't above the minimum height. The sample needs to basically be below this level, otherwise it may crash into the electron beam. So, the tip at least. Okay. So that's good. In addition, while I'm closing the chamber, we have a camera inside the chamber that lets us see if the sample is actually going to run into the source of the electron beam, which is right here, that conical piece right there. So I'm going to close it carefully. And now I'm going to pump down. Now that we've evacuated the chamber, we can turn on the electron beam and therefore generate an image on our monitor. So I'm just going to click the button, and it'll take a second or two. And there it is. So that is our image. You can see it's wildly out of focus, so I'm going to spend the next couple of minutes just focusing the image and also raising our platform to the proper imaging height. We're going to magnification 2000. So I'm just focusing the image here. So you can see I can bring it more in focus, or if I go too far, it's back out of focus. So like this, looks good. I'm gonna auto contrast the image as well, so it's not so bright. Now that's a bit more reasonable. So now this is focused. So now I'm gonna raise the platform to 10 millimeters. So we're gonna see it go up now. Well, now, if we look at our image again, we see that's out of focus again. So I need to refocus, and then we'll make our final approach to 5 millimeters. Yep, this is pretty good. Now we're going to raise the platform to 5 millimeters now that the image is in focus. Now that we're at the proper operating height, I'm going to make sure that we're in focus, and then we're going to go ahead with our EDX experiment. So what that means is I'm going to magnify to way higher magnification I need and just make sure that that's in focus. And then we'll actually zoom out to a point that's actually useful for our experiment. Here we go. So you can see that even though the film may have looked continuous to our open eye, we can see that there's a lot of these individual grains. They're very different sizes, shapes, and this tells us important information of how the film actually forms. And how this film forms will directly affect solar cell performance. Right now we're at about 20,000 magnification, but I'm going to move back to about 5,000. And then I'm going to move the sample to a different part. This is good. So yeah, something that you can see in the film that's obvious is there's a lot of holes. In the film, it's not a continuous, clean sheet. And as I said earlier, that would be a major problem if you're trying to get a highly efficient solar cell. Ideally, you just want a perfect, flat film. All right, so we do all of our EDX experiments on this monitor, and we use a program called Aztec. So I'm going to launch the software now. All right. So I'm just going to create a new project. And yeah, we'll just call it Project 1. I'm going to save it in my folder. Do that really quickly. EDX video. Say OK. All right, so now we have the software up and going. So now the next part is I need to turn off the CCD camera because the camera itself can actually interfere with our EDX experiment. So we won't be able to see in the chamber, but that's okay for this experiment. So what we're going to do here is actually insert the detector. Typically it's left out for normal SEM operation, but we need to actually insert it and make sure the detector is a bit closer to our sample so we can collect our data. So I'm going to click here and we're going to say in. And when I click this, we're actually going to see the detector over there move in to the SEM. So first what we do is we have to select an electron beam energy, how much energy our beam has. So in this case, the signal I'm looking at for lead, the energy transition I'm looking at for lead is, that actually has an energy of about 2.3 kilo electron volts, while for iodine, it's about 3.9 kilo electron volts. And so that means that I need to make sure I have an energy that's higher than that to make sure I actually excite the sample properly. Otherwise, if our energy is too low, we won't see the peaks that we need to see. So typically what we do in EDX is we need to set the energy about 2 to 3 times above the largest peak we're looking for. This is called an overvoltage. And so I'm going to select an energy of 10 kilo electron volts since our highest energy was about roughly 4 kilo electron volts. So I'm going to do that on this screen here. I'm going to go to beam 10. We're going to do a little bit of refocusing as well. All right, go back to this magnification. All right, so now we're at a proper beam energy. And now I'm gonna go ahead with going through some of our settings. And so in this case, I'm gonna take care of some settings that are important just for our overall experiment. First is our energy range. Basically, what range of energies are we looking at? Since the energy of our beam is only 10 kilo electron volts, I'm only going to measure up to 10. And in addition, we have something here called a process time. Process time is the amount of time required to average each change in voltage resulting from X-rays incident on the detector. A longer process time means more resolution between two peaks with similar energies that can be achieved. There's an optimized process time. If it's too short, we're going to have really poor resolution between peaks. If it's too long, the detector is going to be overwhelmed with input. So what we actually do is we deliberately introduce some dead time, or some time when we're deliberately not letting X-rays come to the detector. What we can see here is our dead time is 2%, really small. That means that we have a flood input right now. So what I'm going to do is change the spot size. Like this. And now we can see that our dead time is about 30%, which is within our acceptable range of 25 to 50%. Now that we've taken care of these settings, we're going to go ahead with taking an image. And now we're going to do that actually on this monitor. So I'm going to click Scan Image. I'm going to check the settings specific to taking a picture. We can see if the image scan size is about 1024 pixels. That's your density of pixels. And yeah, our dwell time is basically a measure of how fast we're going to take this picture. Shorter dwell time means that it's going to be a faster picture. In this case, 5 microseconds is fine for this. So we're going to say start, and we're going to get an image that shows up right here. And now we need to actually acquire spectra. We need to figure out the composition. So there are many different ways that we can actually do this. One option right here is called Point and ID, where I literally just click on different points, and we're going to measure the composition at that exact point in the image. So first, to acquire spectrum, I'm just going to click on 2 different points. Usually I'll do a bit more, but we'll click one here and one here. And now we can see the peaks right here. So each of these peaks, our x-axis is kilo electron volts. Our y-axis is just counts per second per electron volts. And you can see we're getting all sorts of peaks here. And so the experiment is, you can see in our progress bar, we're almost about 2/3 of the way done with the first point, which is right here. And that's going to automatically go ahead and calculate the composition at the second point. And you can also see that our output is actually much higher than our input, which is, in this case, generally a good thing. This is a direct result of our dead time, deliberately cutting out some of that input to maximize our output. So the experiment is done. So I'm going to click on the next one, which is the next tab, which says Confirm Elements. And what we're going to do here is just confirm all the elements that were detected by the experiment. So first, we can actually see that our biggest atoms were silicon and oxygen, 2 atoms that we haven't even, we're not even really looking for. The reason silicon and oxygen are such big peaks is because our substrate is glass, or in this case silica glass, which is composed of silicon and oxygen. And what this should immediately tell us is when we're doing EDX, we're not just measuring the surface, the surface composition. We are measuring into the bulk. So far into the bulk, we're going past the perovskite into the substrate itself, into the silicon oxide. And so in fact, much of our EDX signals actually come from the substrate rather than the perovskite film that we're interested in. So what I'm going to do here is just confirm the elements, and we can see that what we generally want to see is that this pink line right here matches the yellow experimental data. The pink line is our fit, and we want to make sure that it's as close to the fit as possible. And we can see that's generally true. So now we're going to go to, and actually I'll go through all the elements too. We can see that we're picking up some elements like sodium, magnesium, aluminum. These are likely arising from impurities in our substrate. They usually show up when I use a glass substrate like this. We can see gold right here, palladium right here. That arises from the fact that I sputtered the film with palladium and gold to make sure our sample would be conductive enough for this experiment. So I'm not surprised to see those peaks as well. And fortunately, we can also see some potassium and calcium as well. Once again, more impurities in the substrate. But we can see that we were able to detect our elements of interest, lead, and we can see a series of iodine peaks. We are now looking at the atomic percentage of each element. As we can see, silicon and oxygen dominates. Now iodine is 4.3 and lead is 2.2. So roughly that means that we actually only have twice as much iodine as lead. So a 2-to-1 ratio, but we are really looking for a 3-to-1 ratio. And so this raises some questions. This makes me think, well, is this a perovskite structure, but we're missing a lot of iodine? Or does it mean we just have strictly lead iodide, which would be a formula of PbI2? So we'd see that by taking this compositional information, we can know the relative amounts of atoms. As I said before, we need to couple this experiment with an experiment that allows us to determine the structure, and that'll give us more insight on what's going on. For example, if we get the structure of a perovskite, then we know, okay, chances are we're lacking a lot of iodine here, but we have the right structure. Or if we get the structure for lead iodide, then we know that we didn't even make a perovskite and something got messed up in our deposition process. And we can look back and figure out, well, what can we change in our deposition process to get the right film? So that is how we calculate composition. What I'll also do here is some elemental mapping. So I'm gonna change this to map. We're gonna use the same image as before. And now we're gonna acquire some map data. So we'll start here. And we're gonna see what we're looking at here is this is our SEM image, and these are the elemental maps for each element that's automatically detected by the detector. So we can see, for example, that we have an equal distribution of, say, sodium and magnesium and silicon and oxygen, and that's expected because those are, that's all coming from the substrate. So that's not very surprising. What I'm actually going to do is get rid of these because they're distractions to what we're really looking for. So we're left with the iodine and the lead. And as you'd expect, you can see that the holes in the lead and the iodine mapping matches that with the SEM image pretty well. So that we know, so the information we gain is these holes right here. We know that these are actual holes in our film, not just, there's not perovskite underneath or anything like that. We know that these are just legitimate holes that go straight to the substrate. And so, yep, and you can see that we're, in this image, we're overlaying the iodine, the purple one, and the lead, the yellow one. And basically, we just keep collecting data until, until we want it to stop. And usually it's about 2 or 3 cycles. So I'm gonna stop this now. And so this is a way where you can actually, map our distribution of atoms as well. So then what we can do is we can export the data, and there's a bunch of different report templates. You can just save the graph, save the compositional data. There's a whole, all these combinations of data that you can export. But after that, you have the data you need. Go back to the drawing board and figure out what happened in our experiment. So this concludes the experiment. We're going to shut down the experiment and remove our sample. And so I'm going to turn our camera back on the CCD, and then I'm going to move the detector out. I'm going to click this, and we're going to click out. And we're done with the EDX part. So now we just have to shut down the SEM like we normally do. So what that means is we first turn off our beam. So the image should go black. No more electrons are impinging on the sample. I'll reset the settings to the default settings. And then I'm gonna drop the platform from 5 millimeters to 30 millimeters, and we'll be able to see that on the CCD camera. So I'm gonna do 30. Yep. Now we're gonna drop it down. All right, now that it's dropped down, we can begin venting the chamber again, and that'll take about a couple minutes. So we're gonna fill it back up with nitrogen and bring it up to room pressure. Vent, okay. All right, the chamber is vented, so now we're going to remove the sample. Going to turn the set screw, make it loose, so I can pull out the platform easily. All right, here's our sample. Now I'm gonna push this back in. Thank you for watching this CEI sponsored video of EDX and its applications to solar related research. I'd like to thank Sean Taylor of the CEI, Scott Broswell of the MAF, my advisor, Professor Alex Jen, as well as the CEI, the MAF, and the University of Washington for their support in making this video. Thank you for watching.